Good afternoon, everybody. I'd like to welcome you all to another edition of the PEM and REM webinar series. My name is Lisa Naich. I'm the Associate Publisher for PEM and REM magazines. And today we're going to be covering the safety effect, understanding the relationship between safety and equipment reliability programs. I'd like to introduce you to the people who will be providing the information today. Our guest speakers, Mike Schultz, the Vice President of Solutions for Asset Performance Group, and of course our editor, Rihanna Begg, will be moderating the event. Just to go through a little bit of technical information before we start, you can ask questions by entering your question in the Q&A box and click submit. We will get to them as quickly as we can. And just a note that we'll be archiving this webinar on the PEM and REM websites within 7 days. You'll receive an email to anyone who has been registered for this, so you can download it to save if you wish. And should you have any technical problems during the webinar, you can either click on the Help tab at the top of the page, or you can send us a question from the question window, and we will try to get to that as soon as possible as well. At the end of this survey, you'll see an exit survey come up, and we would really appreciate it if you could, at the end of the webinar, there'll be an exit survey come up, and we'd appreciate it if you could take a moment to answer a few questions that will come up on your screen. We use this input to help plan future webinars. So before we get going, I would really like to say a thank you to our sponsor, Parker Canada. We take a moment to listen to them.
At Parker, we're partnering with our customers to develop solutions that advance our world. Together, we can engineer a higher quality of life. Parker, the global leader in motion and control technologies.
Good afternoon. Welcome, everyone. Welcome to the 2015 PEM webinar, The Safety Effect. My name is Rihanna Begg. I'm the editor of PEM magazine and REM magazine. In this webinar, we want to explore the relationship between safety, equipment, and reliability. So it is my pleasure to introduce Mike Schultz, who is VP Solutions at APG, Asset Performance Group. Mike is a certified maintenance and reliability professional, maintenance management professional, and industrial mechanic. He's a longtime advocate and practitioner of reliability-driven performance improvement. He was formerly a senior corporate reliability specialist and a 30-year employee at ArcelorMittal Dofasco. We are delighted to have Mike, particularly for his extensive real-world experience in developing and implementing performance improvement solutions. Welcome, Mike. So let's set the framework or context for this topic. What exactly is the relationship between reliability and safety?
Thank you, Rihanna. On the 23rd of March 2005, there was a catastrophic explosion at the Texas City refinery. The ensuing fire took many hours and days to put out, and in the end 15 people were killed and 180 injured. Windows up to 3/4 of a mile away were shattered, and fundamentally the investigation showed several root causes, some of which were related to procedural issues, but in line with our discussion today, it was identified that there was in fact a defective high-level alarm in the splitter tower, a defective sight glass that was used by operators to understand fluid levels in the splitter tower, and a vital splitter tower level transmitter which had not been calibrated. Fundamentally, over the next hour or so, our discussion is going to be about understanding those risks and that relationship between those discrete pieces of equipment and the significant consequence, which we would all agree is really the impact on health and safety, and also factor in environmental integrity with that. So we're going to look at consequences and equipment criticality in this discussion. I want to spend a little bit of time talking about elements of relative risk and what that is, and how that can be a wonderful input into the design of a risk matrix where you're not to have one presently. I'd then like to draw that connection closer to age and life-related failures versus random, and some discussion around that concept, how risk and reliability decisions need to be made, and finally, a brief discussion on strategies and tactics to manage risk. I want to start first by grounding ourselves in what, at the end of the day, customers are most interested in. Any customer in most discrete manufacturing facilities, at the end of the day, want quality product. They want it at a reasonable price, and they want it delivered to them on time, and sometimes they're interested in some service elements. From a manufacturing perspective, we deliver those things by meeting these principal organizational objectives, and you can see first and foremost that connection to safety. Safety and environmental integrity are critical in most environments and industries these days, but there's also a focus on providing a quality output to meet the demands of the customer, moving enough product through the process to meet both the delivery targets and remain profitable, and last, doing that at a cost which ensures a margin. We have equipment in place that delivers that. It's thought of as happening in a couple ways. This first concept of instantaneous capability is really about making sure that at any point in time, the equipment can deliver those objectives and certainly exceed the requirements of the customer. We ensure that instantaneous capability through asset care plans. And certainly operators have a role to play as well in terms of their own operating procedures, and then directly to the organizational goals in the ways in which they operate the equipment. Engineering and technology has a role to play with respect to equipment improvements, where the equipment is now unable to meet the higher objectives, and hence changes and improvements need to be made. So I think we can see that indirect connection from asset care plans and procedures to the safety organizational objective.
So, Mike, let me ask you, who has the greatest impact on reliability?
Well, that's a really good question, because from a risk perspective especially, and unfortunately we saw in the Gulf of Mexico fairly recently with respect to the oil rig fire, we would have initially looked to maintainers and operators as having that big impact, but it didn't take long before escalation took place, literally right to the top of the organization's CEO of British Petroleum, who had to step up and accept accountability. So my opinion is that there's a role for everybody to play, from the most senior ranks right down to individuals in the grassroots of an organization. And really, it's about trying to manage risk, which is defined here as the identification and assessment and prioritization of the things that can cause these kinds of events. We want to coordinate and understand how we can apply resources. We want to minimize and monitor, and at the end of the day, maximize opportunities. This is a formal definition of risk management. And ISO themselves identified that this is such a critical piece in large manufacturing organizations that they developed a standard in November of 2009, ISO 31000, which helps to provide principles and guidelines. But it doesn't give the exact how-to. So in our discussion today, I'd like to talk a little bit about that.
So what we want to do is we're going to put up a poll right now, and we're going to ask our participants to just respond to the question, what is the state of your safety program? And Mike, you can continue talking to us. And once we have some feedback, we can refer to the results.
Excellent, thanks. So failure impact then is most simply defined as this combination of an event and a consequence associated with the event. So we'll deal with consequence criteria and rankings first. To understand failure consequence, we must first lay out what criteria are important for the business factors of your organization. We saw that in the previous slide, where we dealt with what are the most common criteria to understand the consequence of failures: impact on safety, environment, what kind of availability is we have in the process, impacts on quality and cost. We see, though, that this can be quite industry specific, and in fact, in some corporations, reputation might be a really big deal. We deal with the travel industry right now, maybe cruise ships as an example, who've suffered some unfortunate incidents of late, and reputation to them is a critical factor. Other folks deal with regulatory and compliance issues, especially in the area of utilities like water, wastewater, and electrical generation and distribution. And so the idea is that we would understand what those criteria are, put in place some kind of stratified and weighted scoring for them, and then provide qualitative examples so that people can understand where they rank.
Okay, so based on, can we just go back to the poll results? There we go. What we see on the screen right now, I'd like for you to provide some input, Mike. We see that of the participants, those who have, let's see, but 55% say that plant maintenance safety is enforced through planning. We have 18% of our participants say that reactive maintenance is important to them because we rely on our instincts. And interestingly, there 27% say proactive maintenance safety is embedded in all levels. Where do you think? Okay, what picture does this paint for you?
Well, I'm really happy to see that nobody said what's a safety program. So that's a good news story. The others are breaking out as I have typically seen over the past 5 or 10 years. There's certainly been a huge increase in improvement around safety and safety programs or safety management in general. And I think the goal would be to move to that proactive approach, but it's nice to see that the vast majority of folks are putting things in place and enforcing and reinforcing those practices. What we're going to talk about here are techniques and methods to perhaps take us to the next level. So with respect to the consequence definement and criteria, we would really want to establish what those criteria are and then put in place some kind of matrix which describes the different criteria. And this is just a simple example that I have for the purpose of discussion that deals with those 5 principal elements. We can see those criteria across the top, and then a weighting scale has been put in place where we weight heavily the safety and environmental elements along with the more operational components. And then we can see that in fact they de-escalate down using qualitative descriptions, and people can grasp this when being polled or asked where a particular failure event would fit in. A simple example of a water distribution system for the purpose of exploring this further, I've pulled out 3 pieces of equipment from that hierarchy of equipment. We see the duty pump and motor number 1, which is running all the time, along with number 2. And then we have a fully redundant standby pump and motor, which is going to come into service when required if there was a failure of 1 or 2. And then the pressure safety valve. Were we to explore across those categories what impact the duty pump would have on those criteria, we would find that for the most part it had a minimal impact, virtually no impact in safety in the environment, and only a repair or operating cost associated with its failure. And that's because we have a standby pump that can be activated and pick up the service and not have any interruption. However, the standby pump itself then, were it to not fail, were it to fail when it was required because of failure of the duty pump, we see a huge impact on the ability to deliver product and impact on the quality element. Customer service could be impacted in terms of late delivery and a higher cost. So the consequence calculation for criticality assessment is really a summing of those principal categories. The pressure safety valve shouldn't be of any surprise. We see that it has an enormous impact on health and safety, and because of the weighting, shows to be quite a large value. And there would be other impacts in production associated with the downtime through some kind of investigation. So this shouldn't be a huge surprise that out of that list of equipment, the most important or the most consequential equipment we have is the safety valve. It might be interesting to see what an enormous difference there is between the standby and duty. In a lot of places I visited, they tend to put heavy maintenance and reliability focus on the duty, and the standby can be somewhat ignored. So that's a complete reversal of what the situation should be. The value of this exercise is then being able to take those individual discrete consequences and really aggregating them together into a collection of criticality rankings. This will allow for the generation of a criticality number. Virtually every modern computerized maintenance management system has some kind of criticality value embedded within its equipment hierarchy, normally a numeric value between 1 and 9. And you can see that a mix or a blend of the different categories can provide now an opportunity to rank individual or discrete pieces of equipment across that entire list. So the message then, the takeaway from this part of the evaluation is, first of all, consequence is an interesting factor. It's a static thing. When failures occur, have the same consequence unless we do something to minimize the impact, probably through a change in how we operate or a change in physical design. But if not, that really doesn't change. The value that we would derive can be broken out at a component level of detail, which is very valuable and can be an enormous help as an input into other subsequent analyses. What sort of critical spares do I need to hold on hand? What am I looking at from a life cycle perspective? And other analytical tools to explore reliability further. And one of its most powerful uses is in the form of prioritizing corrective work backlog. It's very good to have a healthy backlog, but where you run into situations of not enough resources to perform a particular job, criticality ranking can be used as a tiebreaker.
So, Mike, this makes me think, though, where should the reliability safety initiative, should it be operator driven?
Interestingly, the reliability and safety initiative really needs to cross the whole spectrum of traditional operational pillars. It's often thought to be the maintainers or the maintenance pillar that has direct responsibility for this function. But if we again recall back to those consequence criteria, we're asking people about quality, we're asking people about customer service. And if we go right back to that triangle diagram at the beginning, there was a role to play by the technology and engineering folks in increasing capability. So the answer is actually a triad of operations, maintenance, and the engineering technology function to take accountability for this. Risk is a different thing. Risk is, in fact, a combination of the likelihood of an event versus or in relation to its corresponding harm. Risk can be expressed mathematically as consequence times probability, so it's the product of the two. We spent a little bit of time earlier exploring the consequence side or the criticality side of the equation. Now, in this case, we're looking at that same failure event, and we're going to try to understand how often it occurs. We would develop a quick table with some qualitative references and derive those into a numeric value. Failures occur daily. That's a 9. I haven't seen a failure here in 10 years. That's a 1. And then there's all the stratification in between. With this in place and this agreed upon within a given industry, because each industry can have different rankings depending on how their equipment is oriented and operated, we can now take the original work that we did, the total consequence score for those 3 items, and simply ask the question, how often have we had problems with the duty pump? Here's where we need that operator input, where the maintainers on their own might not have all the answers. The operator is directly linked with that equipment and says, typically we've had issues with that equipment about once a year. So we would end up with a failure ranking of 4, and the product of those is a relative risk of 8. Ask the same question for the standby pump, and we find that this particular pump is actually quite unreliable. Standby equipment tends to be ignored. Standby equipment is also a wonderful parts source. I can't tell you how many times I've heard stories of people going to start a pump and motor, and the motor is missing. It was a wonderful replacement for something else. So we see a high failure rate resulting in a much higher relative risk, and this is perhaps the surprising factor as well. We know that the pressure safety valve is extremely consequential when it fails. However, it's a very well-maintained and well-understood device and may have a very low failure rate. The takeaway from this slide is really about understanding that it's not just about consequence. We need to look at that probability element, and from that, we can take those bits of information and we can overlay them into a risk matrix, which will help to understand some prioritization and where this equipment falls. If this is absent, I would strongly suggest that large companies spend the time necessary to put it together, and then the overlay of both your probability of the event and your consequence can create some nice color-coded areas where risk is considered tolerable but also intolerable. With respect to risk, again, in a similar fashion, what are its uses? Well, risk is a dynamic factor. Risk will change and is constantly changing. Its 2 biggest impacts are the effectiveness of a particular control. This control is good versus bad or useless versus effective. And then adherence. We see many instances where controls are in place. There are excellent PM programs and other forms of procedures and strategies. They're just not being adhered to. Relative risk provides us with a method to identify where the gaps are. If you remember that risk matrix again, we would find things that end up in that top right-hand red corner, which is considered intolerable as candidates for improvement projects. And if it's deemed to be an equipment-related primary causation or cause, then we would feed that into a continuous improvement process for our reliability program. Risk can also be a very valuable tool when looking at instantaneous probability methods to decide which PM I have to do right now. I'm not a big advocate of deferring the preventive side of your program. However, there are instances where that must happen. The risk on it, based on an instantaneous probability, is one method that can be used to understand what risk you're willing to be exposed to.
Okay, so at this point, I'm going to pause for a second and ask our participants to take a look at another poll. It's a quick poll, and based on what we've now heard, I'd like to ask people: safety and reliability policies and programs should be formulated and developed by which part of your organization? Should it be managers, qualified specialists such as planners and engineers, the people closest to the assets, or is it a mix of the above, all of the above? So I ask you to vote now, and we'll ask Mike to give us his perspective on what your responses are.
Excellent, thank you. Yeah, the risk and criticality assessment process does have a caveat. Care must be taken to ensure that these assessments are applied to an appropriate level of detail. I have a couple quick slides here to illustrate that. Most people have a minor fear of flying, or they understand the consequence of a failure in an aircraft. If I was to ask the question, what kind of consequence would we get from aircraft failure? Certainly we would consider that to be deemed high if I asked high, medium, or low. But then the danger here is because of the level of detail. If I asked someone how many failures we were having on an aircraft at any point in time, that would also be high. That could be something as complex as a bearing in the jet engine, could be something as minor as my seat won't recline. So at that level of detail, we don't have a lot of use associated with the output. If we move down at a system or subsystem level detail, we can now start to see that we can discern or differentiate between different relationships between consequence and probability, and start to be able to make some assessments as to what the next steps should be or where we should go.
Okay, so at this point, we're going to bring back the results. So what we see is that, oh, look at that. 93% said all of the above. Mike, where do you stand on that?
Yeah, I would. I think that was a fairly easy question, and it's nice to see. But certainly the idea here is that there is a role to play for your safety program across the board. Managers have a role in setting policy and direction. People closest to the assets and specialists can provide that direct feedback and take accountability for their own safety in the context of that equipment. So the question comes up a fair bit when I show this slide about moving to a system level of detail to make these assessments. Do all assessments have to be done at this level? Well, frankly, the answer to that is actually no. There is a myriad of tools and methods to assess the two principal points of our discussion today. First of all, the safety element in the context of process risk, and then equipment reliability in the process of improvement. We've got hazard and operability studies, process hazard analysis, powerful tool, layers of protection analysis, risk register to understand what's in place. It's really the collection of those tools that is going to provide the answer, and they will work at different levels of detail within the overall asset base. As for the equipment itself, we've got a number of tools, again, from certainly traditional reliability-centered maintenance, which is one of the best overall improvement methods, but then risk-based inspections for your static equipment and your safety equipment, RAM analysis, especially in the early days as it relates to understanding maintenance for a new greenfield facility, or in the context of things like large turnarounds and what do I need to do to be prepared to meet my goals and needs there. And even bad actors identification or root cause failure analysis has a role to play, albeit on the reactive side, it's still a critical tool within the overall spectrum of things we can do. And I don't want to sort of slant this to think that if I do a risk and criticality assessment, I've got all my answers, because that's not the case at all. What reliability roles play is that the risk and criticality assessments will provide identification of the risk exposed in those assets. We talked already about the power of using it for backlog management in the corrective and PM world. It's an excellent input into those other risk management tools, which are critical as a part of an overall strategy and the prioritization of improvement across the spectrum. From an equipment reliability perspective, we see analysis and implementation of reliability controls as being critically important. The development of formal asset care plans in a proactive fashion, understanding what critical spares are required to have on hand to minimize some of the consequence, procedures, and improvement recommendations across the board are all a part of the program that we want to deploy.
So, can you talk to me about the proof that we have for this relationship then?
Oh, that's a tough one. One of the difficulties associated with this relationship between equipment reliability, and I know the focus today is in the context of safety, but I have broadened that already to include environmental integrity and operational capability, is that really what we're dealing with are measures around avoidance, and measures of avoidance are very difficult. If I hadn't have done this, would I actually have had the failure? Now, some things are really solid. Other things are less solid. I think to Y2K. After the year 2000, January 1st, 2000, everybody said, boy, all that money we spent on Y2K preparedness was a waste because we didn't have any catastrophic failures. But then you could counter that argument with, I didn't have any because of my mitigations. There certainly are some general proofs in the industry. Commercial aviation absolutely proved in the 1970s that enhanced identification, understanding of risk and criticality, and certainly the use of formal asset care plans took aviation from 60 crashes per million takeoffs down to 2. 60 crashes per million takeoffs is a crash of a 747, 2 every single day. So we're certainly not living that anymore, and I'd like to give a fair bit of credit to both the engineered improvements, as we talked about in the first diagram, but also the care plans and the understanding of the risk associated with that equipment. So when it comes to asset care plans, there really is a combination of proactive tasks that you need to put in place to reduce or eliminate consequences. And this is that nice tie-in between your PM program and your assessment, because at the end of the day, every PM we perform is about consequence mitigation, not necessarily eliminating a failure. When we deal with failures that have safety or environmental consequences, and we can't find a care plan that is going to manage that to a tolerable level, once again, referring back to that risk matrix, then we need to look at other things like one-time modifications or other procedural controls to manage that more effectively. So failure causes and consequences, then it's fairly obvious that it's critical that when we have a failure condition that can affect safety and environment, we must put in place an effective control. It's also, though, equally critical to understand how equipment behaves, and I'd like to spend a few minutes exploring that a little further with this slide. Just a general question that I'll throw out there to the group. As equipment gets older, it is more likely to fail. True or false?
Okay, so at the same time, we're putting up the poll right now. Okay, there you go.
Excellent.
This next question.
Yeah, so this is the question I'd like to pose, and I'll answer it. I will answer it for you while you're voting on this. I think it's fairly reasonable to say that over a period of time, as we have equipment in service, we would expect to see a certain amount of failure, and we're going to sum that up in this concept of a conditional probability of failure as equipment is in service, and it will reach this natural point where we'll start to see an escalation in the number of failures occurring. We would normally categorize that as being a wear-out zone or perhaps an end-of-life zone. And if we put in place mitigations and methods to manage that by perhaps intervening with a replacement or an overhaul before that end of life, we should have a very robust and wonderful strategy. Mm-hmm. That just makes so much sense, and ironically is so wrong.
There you go.
And I see the poll is back up, so maybe we'll speak to that briefly.
Right.
71% appear to have saw the logic in that concept, and the diagram seems perfectly logical. And we use these terms in our own life where we say things like, geez, it must be reaching end of life, it must be worn out. But in reality, things don't work that way. In reality, things fall into one of these 6 failure pattern categories. These were derived and developed in that study that was performed by commercial aviation that resulted in the reliability-centered maintenance tactic or method or methodology. And interestingly, for an aircraft, these were the actual percentages of equipment failure associated with the components. Quick math will show that in fact 89% of the components on an airplane in the 1960s conformed to a random failure pattern, that there was in fact no end of life. Once again, ironically, pattern B that we described a minute ago only accounted for 2% of the components on an airplane, yet at that time, more than 80% of the components were on a scheduled age or change-out frequency. This accounted for a number of issues. It meant that we were either intervening too early or too late, and if we look at pattern F and A, we see high infant mortality. Our intervention itself actually increased the probability of failure by reintroducing infant mortality into a stable system. So in reality, the answer to that question was false. The vast majority of components do fail on an age or life related basis, and therefore they had to come up with different strategies to manage around that. What is currently believed to be the 3 formal methods for proactive maintenance is predictive maintenance, preventive, and functional testing. The preventive maintenance actions are scheduled events that would occur on a time-based frequency to either replace or repair overhaul equipment. That, of course, as we know from the previous slide, is really only technically correct in 11% of the equipment in service. The other 89, because it does not have an age or a life, must have other methods to manage it, and we see the use of predictive as being one of the tools that has been developed of late to help us in that regard. Predictive is different because predictive looks at equipment and tries to find those failing indicators. I'll just quickly analogize to the human body. I don't think anyone here, although we might have an average life of 72 to 76, I don't think anyone here would schedule a heart replacement at 71 years. But what we might do is keep an eye on blood pressure. What we might do is keep an eye on cholesterol. What we might do is even use auditory senses and have a skilled doctor listen to my heart to find indicators of failure. And it would be based on those assessments that corrective responses would be put in place, not based on pure time-related change out or rebuilds. So that's the power of the predictive, and the predictive aligns so perfectly with the failure patterns, which are 89% random, and also aligns beautifully with our desire to put in place controls to keep our equipment stable, and in this context, keep our equipment safe. If we had have performed that calibration on that tower that we talked about at Texas City, we may have brought that sensor back into calibration, and we may have received the information necessary to respond accordingly. Had we performed our alarm function test, which was found to be in a failed state as a part of the analysis after the failure, we would have identified that alarm as being defective and fixed it. And it would have provided alarming, which would have almost certainly caused the operators to stop the startup of that refinery. So the functional testing and the predictive are really the forefront of where we want to go in an asset care plan to manage around serious or consequential risk. And on occasion, we do run into routine maintenance tasks that aren't technically feasible or worth doing. We do have other options associated with those. We would look at run to failure policies, which could account for a large number of actual failures that are inconsequential. your cigarette lighter in your car, as an example, might not have a formal maintenance strategy. We would look to redesigns, physical or procedural changes. And then perhaps in relation to our earlier discussion on consequence, physical changes to the device to reduce the consequence associated with the failure, especially again if it has safety or environmental consequences, to move it out of that realm and something more operational, or make redundancy or physical changes as necessary to make sure that we're working in the tolerable range. So in the end, the relationship between safety and equipment reliability is a fairly stable one. The first part of this assessment should really be around understanding failure, consequence, and risk, as we discussed. Get started to be clear on what risk we're exposed to based on failure rates and what kind of consequence will occur if a particular failure event takes place. Then from that, we would also want to identify appropriate reliability controls to manage risk and make sure that those controls are in place. Why would we be interested in doing this sort of thing? Well, at the end of the day, it's accountability for safe operation of those physical assets. The question that was asked earlier related to who is accountable. Well, it's right from the bottom ranks to the top. And at the end of the day, it's also about meeting the stakeholder needs and wants. Beyond the safety and environmental question, unavailability of equipment means it's not in service. It means we're not making money. How would we do this? There are really some fabulous best-in-class tools in place for assessment and management of risk, and we want to deploy those as a part of an overall proactive strategy. And I really can't underestimate the importance of that in fact we want to have a full-bore strategy in place which utilizes the best tools at the right time, understanding both the limitations of the tools, perhaps limitations of the data that we have in place, but as a part of a long-term strategy to move in the direction of proactivity in which data gathering will continue to build and allow those things to be more effective. What benefits would we see from this event? Well, the most obvious one is meeting those safety and environmental targets that were put in place, understanding that through the development of a risk register and the development of a risk matrix, and working to move from the intolerable to the tolerable zone. We would also see an opportunity to end up with a lowest cost solution when compared to catastrophic events. It was pretty obvious in the first picture of the Texas refinery that wasn't working for some period of time. It was out of service quite a bit. With respect to the Gulf disaster, that oil platform is on the bottom of the sea and not producing. And you could say that with Bhopal, India, or many of the other serious events that have occurred. So from a pure cost and operability perspective, the benefit is fairly obvious. I also want to mention that this is just good custodianship of physical assets. Things are purchased in your own home, and I'm sure you take very good care of them. Sometimes in the field, people lose sight of that a bit. Somebody else bought that equipment. I don't own it, and that's not good custodianship. Maintainers, operators, the engineering and technical groups, the management teams that are responsible, all have a requirement to take good care of that equipment. And it does go beyond safety and environmental issues, but those without a doubt are the most serious and significant in leading us in that direction. From a risk perspective, there are a couple associated with this relationship. The first one, which I see far too often, is the desire to find a silver bullet. That in fact, if I just do this, Mike, everything will get better. And the unfortunate truth is that's not the case at all. There will probably be some marginal gains. Yes, I would agree with that. But there might not be the sustainability that's required to hold those gains. And you're certainly not going to realize the full potential if you're just looking for one tool. You need a composite set, a collection of the different strategies that we've discussed. And in fact, the development of an overall strategy that blends these things together across a reasonable timeline based on the current status of resource availability and data requirements. The other risk is inexperience in the deployment and facilitation of these tools. There are some complex methodologies here, some complex concepts. I may have simplified them for this example, but they're far from simple. And my strong advice would be to seek out experience in deploying this sort of practice and technique, and make sure that they're being deployed to their full potential through effective facilitation of those tools.
Well, Mike, okay, that's a really good place to end of this presentation. I want to thank you very, very much for a very informative presentation. I must say that proving the value of safety of a safety program, it is an ongoing challenge for industry. Whether you're a safety officer, a risk manager, you're an operator, a reliability specialist. But one takeaway from today is that when we're developing proactive maintenance strategies, we need to effectively manage risk to a tolerable level, as you had demonstrated. And we can do this using a mix of direct maintenance tactics, as you said, modifications, training, and procedures, and these all of which you demonstrated today. So I'd like to thank you for an informative discussion. And Mike Schultz is from the Asset Performance Group. He's our featured presenter today. And I would like to thank our sponsor, Parker Canada, for making this educational presentation possible. And thank everyone who's online and participating today. Should you have any questions, please email me at rbeg@annexweb.com. Your feedback is very valuable, so I ask you to please fill out the survey at the end of the presentation. And thanks everyone for joining us again.